So the next part is going to be how to add light. So in order to add light, we need to understand a little bit more about the form lighting model, right? Or form shading. So if you go there, they have sort of this example. But if I search for shading, I think this Wikipedia article should be something that we can use. So as you can see, form reflection model has three components: the ambient, the diffuse, and the specular. So three components of the lighting. So the ambient lighting is going to be this flat, as you can see, the flat lighting. There is no need for any normals. The concept of direction is not there. But the diffuse and specular, for these two, you need to calculate the normals because there is sense of direction, and based on that, you can see some part of the object is brighter and some part is darker. And the specular is more like the reflection, this glossy part here. So there are more details about, I think, if you go to form reflection model, they have the mathematical equation for explaining all the components. We are not going to explain everything, but we are going to show you how to calculate the specular, diffuse, and the ambient component. I will let the reading up to you. Although just from the name, it is sort of intuitive. But also how the components are calculated is also sort of given here. So you should be able to relate this coefficient, Ks, Kd, and Ka. This is the total light, I, right? So as you can see, the ambient is just this multiplication. And for the other two components, we have more complex calculation. But it's not that complex actually. So if you go here, you'll see how to calculate each of the steps. That is exactly what we are going to do today. But our version is going to be a little bit simpler than all. So we're not going to explicitly use the coefficient, which they have the ability to change in it. But for our case, we're going to consider that all the coefficients are 1 by default. And another good source is, you'll see, but probably I'll show that later. So they have, in the book, they have two examples for calculating the form, something similar to the form. This is not complete, but they show you how to calculate the light per fragment. So first, let us calculate the light per vertex, and then from there, we'll continue. Okay, so let's go back there, and we are going to start working from before going to the shader, we'll start from the CPU side. So we need, as you can see, we need the light, the shading model, and the moving point light. So first thing, you need the overall light. Before the point light, the moving point light, we just need to add a simple light. So that's why we are considering that there is more like a directional light, right? And I'm going to add some component of the light. So I'm going to have the light direction. This is going to be a vector. Assign a new vector 3. And let's say the light direction is coming from 1, 1, 1. You can change the direction later if it works. But for now, I'm just going to use this vector to say that the light is coming from. So this is, if this is 1, 1, 1, so light would come from. So this is 1, 1, and this direction. So something like that. You see some sort of lighting here. Okay, so light direction here. Then we are going to add the related components. We are going to pass the information to the shader. Okay, so we will have a lot of uniform variable that we're going to pass to the shader. And so what are the component? Where are our uniform variables? So let's see. So these are the uniform locations, and we are going to add 3 components first, right? So let's create U ambient now, and then create a let U diffuse color. Finally, I'm going to create a specular color. Specular. So from the name, it's obvious, right? So these are our uniform variables. So now we need to create the uniform variables here. Right? That is similar to how we have this other variables. So let's copy this. Again, ambient color, then diffuse color, then specular color, and same thing here. Okay, so we have these 3 colors. Then we need to send the light direction, right? So I'm going to create U. Create a light direction here. I have this light direction, but I need an uniform variable to pass the light direction. So, okay, we're going to eventually need those, but for now I'm doing those there. And then okay, I'm going to create a same variable here. All right, so this is done. Change this. Now I need to pass the light data to the shader, right? The light data. And it's automatically correcting this, which is wrong. And what are the data we want to pass? We want to pass the So from 3F, we're going to pass the colors. So first thing is the ambient color. Let's say the ambient color is something 1, 2, 2. This is a very low light. Ambient light is obviously should be very low light. Then for each of the light, I am going to use something. So the diffuse color can be a little bit higher, maybe close to white light. And then the specular should be white because we want this white reflective surface. And then we need to use the camera, the light direction. And we already created a light direction here, top. This one, I'm just going to use that variable. So light direction. Yes. Okay. Sorry about that. So now everything is, I hope, settled in the CPU side or the JavaScript side. So I need the similar variables here, right? So for now, I have the color, but I don't have the other components. So I'm going to quickly copy the things I have here somewhere. These are the things I need. Okay, so I also use the hue color somewhere. Before we didn't do any color on the vertex shader. Now I think we'll need that. So let me have a copy of hue color here as well. And each of them are uniform vectors. Moving the null. Okay, so I think we have everything we need for calculating our lighting in the main here. Okay, we need to calculate 3 components, right? So our final lighting, for now our V color is the normal. We are not going to use that. We are going to have the 3 components of, so V color is big 3 so far. So we are going to use, let's say, 3 components. I'm going to give a name as it should be named, and then we need to calculate the diffuse, and then we need to calculate the specular. So 3 components, we haven't calculated them yet, and that's what we need to do. Okay, So we have the GL position calculated here, but we need to calculate. First, we need to calculate the normals in the. So if we go back to the form shading or form reflection model, you'll see these are the components you need to calculate for the form. So let's say all the K's, they are 1. So the first thing is ambient, then we need to calculate the diffuse and the specular. So these are the components we need. And for each of the components, you can see how they're calculated. It is mentioned here. So let's start with the N here. So N is the normal at that point. So we can calculate the N. So let's say with 3 N. So N is actually, we have the normal matrix here. So this is the normal at this specific vertex. So normal matrix multiplied by, we need the, okay, so this normal matrix is the mat4, and we have a normal which is vec 3. So we need to multiply this with this, which is not possible, so we can make it 4 to make the multiplication work, and then the last component should be 1, right? I think this should be 0. Then this is a vec 3. So what we can do, we are going to take only the XYZ component. XYZ component of this calculation. Okay. But we also want to normalize this vector, because this is a directional vector, and we want unit vector for that. So I'm going to normalize that. So this is the calculation of N. As you can see, this is the hat. Because of the N hat, we normalize. So all of this value, we're going to normalize them. And then we need the L, we need the V. So what is the L? Which is the direction vector from the point on the surface towards each light source. So L is, in a single word, light source direction, right? So we have a light direction. So we have to calculate the L from that. So let's say L. Whatever comes out, we're going to normalize that. And L is straightforward, the light direction, because the light is not going to move at this point. So L. Then the next thing is we need to calculate the V and the R. So V, which is the direction pointing towards viewer related to the camera. So we have to do something to related to the camera. So vec 3V, whatever it is, going to be normalized. For this, we need the I position. We need to calculate the vector from the I position to the XYZ position, right? So do we have the I position for now? I think we have the camera, so the I position should be easy to calculate. Let's go to the camera. So we have this I position that we can use for calculating our I position. So let me create another uniform variable here. I'm going to call this I position. And we have to do all the stuff we did here. for the eye position as well, right? So question is, did I already do that or did I not? So eye position is for now. Let me we can assign this as null, and then okay, so yeah, in the draw function, we're actually using the eye position already. So this is the uniform. So we have the uniform variable here, and then we are not, every time we're changing the camera, because the draw function is related to the change of the camera, so we need to update the eye position here, right? And the eye position is just coming from the camera. So our camera has the eye vector. So this is our eye position for now, but it can change because our camera is changing using the control keys, right? WASD. So that's why every time we change the eye position, we update the draw function in our keyboard call here, right? Every time we change something, we do a draw call. That's why we cannot put the eye position outside. We need to put the eye position inside. So this is the place where we are passing the eye position. So we are good with that. Now, the only thing we need to do is we need to create this. So where did we connect the eye position? So we're passing that here. Let me see. So we need to calculate the eye position, then we're passing that from camera. Somewhere we need to connect that. I think I can easily do it here. So let me create this here. Okay, now I don't think this is repeated. That's what I was worried about. So only one found, so should not be a problem. Only thing we need to do is create this here, right? So in this uniform, let's see, eye position. Okay. So we have this light position, we have this eye position, then we need to calculate the V. So the V is going to be the eye position minus, so this is a vector, our world position, which is vector 4. So we need to do x, y, z, the first three components of that. Okay. Then the last thing is we need to calculate the reflection vector, the reflected ray of light, right? So the r. So let me do vec 3r, then whatever it is going to be normalized, since r is hat, r has a hat. And then how do we calculate the reflection? So actually, WebGL shader has a reflect function that we can use to calculate the reflection. And for the reflection, it is a reflection of L and N. Let's see. So this is our reflection. Reflection is L and N. You don't have enough time to go into the details, but let's just quickly calculate that and see if we can make the model work. Okay, so now we have all the three components. Then we need to calculate each of the components, right? So let's calculate ambient. Let's calculate diffuse, and let's calculate specular. For some reason, it's adding the phase 3. Okay, so I want to create functions for each of the three calculations. Okay, so I'm going to call this calc diffuse, and I'm going to call this calc and I'm going to write each of the functions. Here. So this is the time. This is time we start calculating our values using function inside the shader. No, we're doing that. So let's calculate the ambient first. So ambient is straightforward. So we are going to return the blue ambient color multiplied by the hue color. And then we are going to calculate diffuse. So diffuse calculation is from the formula that you see. This is more n dot L, and I'm just going to use the diffuse calculation formula. So we calculate the dot product between n dot L, which is going to be the max value of the dot product of L and N, right? It should be greater than 0, 0. Otherwise, you see, not see anything because this is light, color of light. So max of this, and then you're going to return okay. So for calculating diffuse, we need the values of L, obviously, then N, and then finally the diffuse color we have. And let's use all these things here. We don't use this view here because it will conflict. So each of these are vec 3, another vec 3. I'm just going to call this D color. And then we have LN, fine, and I'm going to return the D color. Multiply with U color, which is always going to happen. Then I'm going to multiply that with N dot L, which we just calculated. Finally, the last is I'm going to calculate the specular. For calculating the specular, we need the reflection vector and the V. So the R and the V. So R so inside the specular we have vec 3 R, locals, variables. And then we need to calculate V. Then max of and so there is a shininess value, a shininess factor for the specular that is also called specular alpha here. So you can see this alpha is sort of, so the more, let's go back to the form, the more shiny it is, you'll see the effect is going to change like this. So it can be 128 to 1. We are going to use some value in between for calculating the specular alpha. For now, you can use a slider, but I'm going to hard code that to make it faster. So what I'm going to do, with the power of S, S is the shininess. So this shininess is going to be W of dot D. And then any value we can use here. Let's use something between 1 to, what is the original value they used? 80. Let's use 18 maybe. Or let's use some smaller value first. 32 maybe. 1/4 of 128. Okay, so this should be a floating point value. Floating point value. And the final thing is we're going to return now. Return what? We are going to return the specular color. Multiplied by the as usual the hue color, and then the value we calculated, I think. Okay. So we are almost close to out of time, but we are also close to be done. Okay, so now we have our V color, which is vec3, and V color is a varying vector, and we are using the V color in the color. So we have V color, and then we have this V color, which is we want to use, right? And let's see if we have something. So we have some syntax error at 43, line 43. So let's go to line 43. I don't see anything here. Looks like we have some extra somewhere around here. Okay, so if this is a typo, then probably going to be really difficult to line 43. Okay, so this is the line 1, so this is line 45 probably. So I'm normalizing that hue light direction. Let me comment out all these things first. This is the probably only way to debug. And we have a bunch of LW required. I can assign all these three as the vec3, and inside that I can make all of this. Oh, I think I see what the issue is. Oh, okay. Okay, so delete all this. I think we have one extra bracket here. Right, thanks. So I will continue and record and upload that. Okay, so we have this this bracket is here, so probably have extra. Okay, so now we have problem with 48. Okay. Yeah, so we never created the variables. So rect3 ambient and now we have something 278. So apparently we have only 2 elements in the light direction. Let's go back to the light direction. Where is the light direction? This is obviously vec3. I don't see any error with that. So we have the light direction. Okay. And so what is the error? It is showing us 4 arguments required, only 2 present. Okay, yeah, that makes sense. So we are sort of passing this as 3f, but we need to pass this as an array. Okay, so here we can see something, although I don't see the proper lighting. Okay. So at least the lighting is working, but the lighting is not bright enough to have all the effect here. That's what you can see. And the light direction may be on the other side. So let's try to pan it a bit. Also need to change the value of the ambient color and see if that changes anything. Yeah, so ambient color is obviously working. That's why it's too bright now. I'm going to so probably the specular color is not working. Let me make the diffuse color a bit higher. Okay, so still very dark. And okay, so okay, so we only see, I think, the ambient lighting here. The other 2 lighting, we may have some bug in the code that need to be fixed. So I'll take a look at the code and fix the bug and upload the code to the files. Also, I may add a note about what bug was there. But since we're out of time, I'm going to stop the recording here. And then I'll upload the video to the canvas. Okay, so after carefully debugging the code, checking the code, I found out I actually missed these 3 lines. That was the reason for not having the diffuse and specular lighting in our code. So we had the ambient lighting before, but the diffuse lighting and the specular lighting, this patch here, it was not showing. And the reason is those 2 components of the lighting, they are directly related to the normal, the vector, normal vector. So since we never calculated the normal matrix, which is based on this formula, we never passed the normal matrix to the normal matrix, right? So here what happened was we created this normal matrix, which is a blank matrix. Then we created this normal matrix uniform value, which was null, and we passed that null value, right? But here we need to calculate that normal matrix based on our model matrix. How to calculate the normal matrix? That is actually coming from this normal matrix calculation article here. You can read through this and it will explain how it is done. So the bottom line of this article is, in order to calculate the normal matrix, you need to take the inverse of the model matrix and then the transpose. This gives you the normal matrix here, as you can see. Once the normal matrix is calculated, you can, just like we pass the model matrix, you can pass the normal matrix. Right? So once these 3 lines are added, now we'll have this normal matrix here. And the normal matrix is required for calculating this NLV, the N, so the normals. So before this one, we actually didn't have any normal matrix. We had a null matrix, and that's why we didn't have any component showing up here. So once you fix that in the code, let's see, if I move around in the word, see. So this is the back side of the object, right? So light is coming from the other side. If I move a little bit ahead, now this is the side where the light is coming from, right? So if I refresh and then zoom in, go forward, then you'll see, so the light is coming from this direction. So this part is the diffuse part, and this is the specular part. So now we have all 3 components. We are done with our lighting here, right? We have the lighting and we have a part vertex shading of the form. So that is something we may do next week. All right, here we go. So this is done, and part vertex lighting is done. So even though we didn't do the form today, still you can check the example here for the form shading, and you will have some idea. So this is what we do today, right? We have this type of patch, and everything for the lighting calculation is done in the vertex shader. Only difference in the form is it passes the value other than the vertex related calculation, like normal and everything is calculated in the vertex shader. But the light itself is calculated in the fragment shader, which gives this smoother lighting effect. So that is something we're going to do next week. And for today, that's all we're going to do. And I'll upload this code on Canvas.